Hi, everyone. It's great to be here today. My name is Professor Jonathan Kelly, and I am an associate prof at the University of Toronto Institute for Aerospace Studies. And today I'm going to talk to you about a topic that's near and dear to my heart. It's the problem of temporal calibration for visual inertial navigation systems. That is the temporal alignment or time delay calibration between two separate sensor data streams. And I'm going to revisit some work that's been presented in the literature on this topic and discuss a bit about why a filtering-based approach to this problem may run into some challenges. Actually, so we're revisiting things that have been discussed previously, and I'm going to hopefully give you a new take on that. I'd also like to thank the organizers very much for putting the workshop together. It's very exciting to be here virtually, and I do hope to see everyone in person in the near future. Just so you know who I am, here's a picture of me in my hotel room since this is a virtual talk. That's me smiling, and again, hopefully I'll get to see everyone in person in the near future. Okay, so the first thing we should discuss is whether time delays in multi-sensor systems between, say, a vision system and an inertial system, whether they matter. So no measurement is really instantaneous for any type of sensor, and usually processing is done in advance in order to remove noise, et cetera, and so there's going to be some arbitrary delay introduced between a camera and an IMU sensor between the measurements in disparate data streams. So somehow we need to deal with that, and here I'm going to introduce our favorite helicopter, Ingenuity, on the surface of Mars. And with this dangerometer on the bottom of the slide, I'm going to claim that as maneuvers get more aggressive with these small helicopters, including quadrotors on Earth, delays do matter, and they do become a significant barrier to a performance. And in fact, they may actually cause a system to fail if you are unaware of the delay, or it's misestimated, or it changes dramatically. The more aggressive your maneuvers with any type of robotic platform, the more out of sync, in some sense, the measurements will be, the larger the discrepancy between the expected and predicted measurements, and the more in danger you are. Now here, of course, our poor helicopter has burst into flames. This wouldn't happen on the surface of Mars because there's no oxygen on Mars, but on Earth, this could very, very easily happen for a variety of systems that rely on multiple sensor data streams for navigation. And so I introduced Ingenuity for a reason on the previous slide, and that is to illustrate with an example here the dangers of unmodeled delays. So interestingly, just before this talk occurred or is happening, there was an issue with Ingenuity on the surface of Mars, and it does rely on a visual inertial navigation system to get it where it needs to go. And it turns out that in this case, approximately 45 seconds into the flight, a glitch occurred in the pipeline of images being delivered by the navigation camera. This was on Sol 91, or the 91st Martian day on which the vehicle was on the surface and deployed. And what happened was that the glitch caused a single image to be lost from the camera. But more importantly, it actually resulted in all of the later images from the navigation system having inaccurate timestamps. In other words, there was an unknown delay that was suddenly introduced into the system. And so the video you're seeing here is of the flight over the ground, taken in the region on the left. And you would expect this video to be smooth, but what's happening here is you're seeing a lot of jerking around, and that's because when the timestamps were corrupted, the result was a very large oscillation that was introduced into the control system, plus or minus 20 degrees in roll and pitch. And thankfully, I'm just looping the video here. Thankfully, the engineers who built the system built it with a large amount of robustness and a capability to absorb some of these types of errors. But if you've worked with quadrotors before, or any type of helicopter platform, you know that plus or minus 20 degrees in roll and pitch is a very large amount of pitch or roll. That's a dangerous amount. And so this is an example of exactly the danger of delays in unmodeled cases. And so I would say certainly the reason why this problem has received some attention in the literature is because delays are not only detrimental, but potentially dangerous, especially when they're unknown and have not been have not been accounted for in the design of the system in advance. So it is worthwhile, I think, to consider the topic. And so now I'll talk a little bit about why filtering might not be the ideal way to solve this particular task, or why we need to think very carefully about how we're doing online delay identification. So just a brief outline of the talk. I'm just going to go over the problem of temporal calibration, or what I'll also call time delay estimation. I've already talked about some motivating examples for why it's important, but I'll tell you about how we typically solve it. Then I will discuss recursive filtering specifically for temporal calibration and why we probably want to revisit the idea of recursive filtering in this context. To support this argument about revisiting recursive filtering and that there may be some concerns in this area, I'm going to show you a very simple system model for an aided navigation application. And it's going to be, in fact, probably the simplest system model you can build. But that will allow us to explore what's happening carefully in temporal calibration specifically, and to see what the results are in a tractable way that is not confused with other variables that we may need to estimate as well. And so it provides a very clear-cut description of what issues arise in the context of temporal calibration with a filtering-based solution in particular. I wanted to talk a little bit about the identifiability of time delays, which actually feeds directly into this problem of filtering. I will discuss some problems with filtering and then launch right into some alternative possibilities to explore. And when I discuss some of the issues with the filtering framework, I'll go over some simulation studies we've done to characterize this very simple system and show you what kinds of troubles might arise in practice with the system you're building. Okay, so again, temporal calibration or time delay estimation is simply the problem of trying to determine what the relative time relationship is between two sensor data streams. So if two sensors measure the exact same phenomenon or same point at the same point in time, right, then there are some unknown processing delays in all of these cases that mean that inevitably when the measurements are time-stamped at the CPU, you have some amount of temporal delay that's relative. It can be either, importantly, a shift forward in time or a shift backward in time, depending on what sensor you're looking at. So typically we would have what we call an acausal case in the real world, right, in the sense that everything has to be delayed from the exact point of occurrence. But because the sensor data streams can be shifted by an arbitrary amount, from the perspective of a filter or some other solution to this problem, the data streams may have an arbitrary forward or backward shift in time with respect to each other. And so that's important to consider. So how do we normally solve this problem in practice? Well, there are a couple of different ways. One thing we might do is try to incorporate some type of hardware synchronization with a physical cable running between, say, a camera and an IMU. And that usually works fairly well in practice. But again, even if you have hardware sync, there is no guarantee that despite capturing measurements at exactly the same point in time, the post-processing of a measurement will actually be the same in terms of the time involved for both the camera and an IMU. And so even with hardware sync, you may have a small unknown delay that's present in the system regardless. So that's one way. And then the other thing we often do is we often try to perform some type of batch calibration algorithm. And usually that involves taking all the data we have and trying to do some type of alignment in time to reduce a batch error function or a batch loss function, and try to do things in that way. And actually, this is some of the earlier work that I'd done and others had done in this area, was a batch-based or a series of batch-based methods to perform camera IMU temporal calibration. So hardware sync and batch calibration are both attractive, potentially, but maybe we don't want to do those in all cases. And so the alternative is good old fashioned standard filtering-based approaches, such as the extended Kalman filter. And what's been proposed is to incorporate the time delay parameter as simply another quantity to be estimated inside of a recursive filter. So the problem with hardware syncing in part is that it might be quite expensive and it may be prohibitive for very low cost systems. It also requires additional, obviously, componentry and so on. So maybe that's not ideal in many cases. And then for full batch algorithms, the issue is that they have to run offline typically. So you don't run a full batch solver online and adjust things. You can do something that's sort of a hybrid, but in general, the batch algorithm is like an a priori type run or trial that's performed, and then hopefully you have the delay parameter locked down, and away you go. Except that, of course, this doesn't allow you to adjust delays online if there is some variance in the delay. So filtering is attractive, of course, because it's easy in the sense that we have a good understanding of at least filtering problems that do not involve delay parameters. And so since many of us in the community, I'm sure many of the people watching today are very familiar with filtering, it just makes sense to try and incorporate the delay parameter. That would be an easy way to do it that would avoid some of these other issues. And the other nice thing about filtering is that you always have an online estimate of the delay quantity, as well as the other quantities that you're interested in at all times. That's great. So indeed, there have been a couple of really nice pieces of work in the literature, going back about 7 years and 10 years respectively, from left to right, on temporal calibration or time delay estimation and time synchronization in aided navigation systems, specifically for VINs and also for GPS aided inertial nav. And these are great. And of course, Kalman might pop in and say, "Hey, Nito, that's my filter." I don't actually know if Kalman ever said Nito, but regardless, this is, it's a modification of his original filtering framework. And of course, Kalman filters are everywhere. And of course, we should also give some credit to Busey for the continuous Kalman filter, and to many others who have built extended versions of the original filter and so on and so forth. But nonetheless, Kalman can be credited for some of the early work, and now these filters have been used all over the place, right? So again, bread and butter in robotics. So we are highly motivated to make use of the Kalman filtering framework whenever we can, and certainly for delay estimation, it may make sense. Now, I'm going to claim later in this talk that there are some caveats and issues to be aware of that are perhaps not obvious when you apply a Kalman filter to this problem in general, as opposed to other problems that involve parameters that are not related to time specifically. Okay, towards that end, I'm going to now introduce a very simple aided navigation system model. And when I say very simple, I mean really simple. And this is going to allow us to explore the problem of temporal calibration free of any unnecessary complexity. So here is the system. I'll call the system Sigma. And it's going to be, as I said, really, really straightforward. I'm going to have just a single state that I care about. That's an underlying state of interest. And I'm going to call that the position. I'll label it as X, but we'll just call it position because we're dealing with, we'll say, aided navigation system, so it makes sense to estimate position. So X will be our position, and the rate of change of the position variable is going to be a function of a single control input only. And in a VINs context, or in this case, what we would call maybe a velocity-based system, because it's a first-order system, we're going to take this control input from what you can assume is some high-rate sensor that drives the process model forward. So this is the one-dimensional velocity-based analog of a VINs system you can think of in one dimension. So we have one dimension of position only. Okay. Then there'll be a single delay parameter that I'll call tau, and that's going to be constant for the analysis that follows, but it's going to be unknown. So we won't know it in advance. That's going to be a quantity we want to estimate as well. And we're going to see how we might go about doing that in just a moment. There's going to be one measured system output, Y, and that is simply the time shifted state. So it's a direct measurement of the output as a time shifted version of the state. And this might make the system look linear, but you'll notice that the quantity in brackets is shifted. It's not a linear shift. It is in fact, a nonlinear problem because of this time shift. All right, and then possibly, if available, I might also give you some knowledge of the state at time t equals 0. But this is a bit tricky because I'm going to say that time t equals 0, which I'll represent here with a superscript 0, x at 0. With the superscript, that's the position at time 0. If I know the position at time 0, that doesn't mean that I knew the position at an earlier point in time or at a later point in time. So that's important. So remember that the value of tau here can be positive or negative. And so the shift may occur in such a way that I receive either measurement updates from the past, if tau is negative, or measurement updates from the future from the point of view of the system. So that's an acausal system, and that may occur as well. Right? So that's something important to keep in mind too. Okay, so that's the system, and then I'm just going to put that in the larger context here of what we're going to do in our aided navigation system, just to show you how things are going to operate. It's a continuous discrete hybrid system. So the underlying system will be continuous, but we're going to get discrete sensor measurement updates. So we'll have a sensor that measures position, but that position is time shifted. And what we're just showing you here is that you see the red lines. There's a regular control input, right, which is our sensor that's driving the process model. So that's U of t sub k, because we're going to treat things as being discrete, but then propagate forward in continuous time. This is exactly what's done in VINs usually. And then you can see here that we're actually feeding everything into a version of the extended Kalman filter, computing the updated state, delay, and covariance estimates using the subscript, k+1 for the next time, and capital letter P in bold for the state covariance matrix. And the state in this case will just include the position x and also the parameter tau. And so here along this line, you can see that we've just done this for illustration purposes. We've got an estimate tau sub 1 with a hat on it that says that this is the first estimate of our delay parameter, which could be a positive quantity, but in actual reality, for the plot here, the value of tau is negative. It's less than 0. So the measurements here are delayed relative to the state. Okay, so now I'm going to bring up the first issue that is perhaps not immediately apparent and hasn't been reviewed extensively in literature. And that is, I'm going to try and show you a very simple argument that the delay parameter in any system requires a finite time for identification. And this is certainly true for the simple system, and I won't argue too much here that it applies to more complicated systems, but indeed, in practice, if you write this material down, you can see that it does in fact apply. And so this just means that usually we consider quantities of interest in the filtering framework to be instantaneously identifiable. And my proposal on this slide is that that is not in fact true for time delays. And so I will show you that in the following way. I'm going to build two instances of that simple system that I showed you, sigma, on one of the previous slides. And I'm going to actually simply time shift the inputs, the U of t's, to two of these systems. So my goal here is to construct two systems that produce the identical outputs over some range of time, say 0 to 1 second in this case. So identical outputs, but for which the actual time delay parameter is different. So again, two systems, two different time delays, but identically measured outputs over a 1 second interval. And if I can in fact show you this, then I would argue that over that 1 second interval, you cannot distinguish these two systems from each other. And yet the tau parameters are different. So this is exactly the definition of identifiability and unidentifiability, right? If I have two quantities that cannot be distinguished over a certain period of time, then the system is not identifiable over that period of time. I can't uniquely recover the parameter I care about until I can somehow differentiate from the measured outputs what parameter is involved, in fact. Okay, so here I've got two different inputs, and if you notice, the tau prime and tau are going to be two different delay values, and I'm going to allow myself to access controls that are just in the interval from -1 to 1. Units don't matter. That's it. So it's a closed set of controls, and they're going to be in that range. And so when I put those inputs into the system, I'm going to choose two arbitrary waveforms, which are sinusoids to input. And you can see here that the portions of the two sinusoids are shifted. So if you look at tau from -2, or tau prime from -2 to -1, you'll see that that is the same, it's exactly the same waveform as from -1 to 0, and those two waveforms are just shifted. And then at the -1 point, I've just simply dropped one control input here, u of t prime, down to be exactly 0 in that interval. And the rose or light pink colored region here is the region that I can actually, in some sense, monitor later on. So, okay, so we'll say that the true delay is in fact -1 second. So tau prime here, -2, will in fact be the wrong parameter, the parameter that we don't want to end up with as our answer. And to show you that we actually can't disambiguate, I will now just visualize what the underlying state of the system looks like, again, over the period of time from 0 to 1 second. So I'll use the notation tau plus for the positive absolute value of the true delay, tau equals -1 second. And if you look here again, you'll see that the underlying states are different, but the outputs, the states between 0 and tau plus equals 1 actually end up looking exactly the same. And so because of that, if I consider the measured outputs of the system, right, remembering that y of t and y of t, or y prime of t, are two shifted versions of the underlying system. If I measure them, without going into too much detail, because I realize it's a little hard to grasp from the slides, essentially what I'm showing you here is that the measured output of the system is identical over the interval from 0 to tau plus equals 1 second. So if you look at the light blue and light rose colored sections, you can see that over the period of time that I am allowed to look at the system, which in this case we'll say is 0 seconds to 1 second, so once the system has started up, over that interval, despite the fact that previously there was a different waveform input, right? There was a shifted control. I can't see that control initially because I have to just monitor the system from some startup time. And here, in this particular case, by construction, we've shown that there are two different systems with different delays that have the identical inputs over 0 to 1 second and identical outputs over 0 to 1 second. And so because of this, because these two systems exist, and in fact an infinite number exists with different delays, because these systems exist, at least up until the 1 second mark, which is the true delay value, I cannot distinguish between them. And you can see here after 1 second in the output plot at the bottom, right, the two curves do diverge and you can distinguish, but you cannot distinguish in that 1 second interval. And so that means when I'm looking at a system, I have to watch the output for at least as long as I think the delay might be after injecting some type of control signal in order to ensure that I've actually managed to capture the true delay. And so this occurs for both causal and acausal systems, in fact, in this case, because of the possible time shifts. And this is a bad thing in general, because we generally assume that we can construct an error in the EKF that is a function only of random noise and maybe some linearization issues. But in general, we don't account for this problem of a finite time required for identifiability or observability. That's not usually encountered. In fact, we usually depend on the underlying system being instantaneously, say, locally weakly observable. And that is in fact not true in this case. Nor is it true for a full-scale VINS either, actually, in fact. Okay, so getting a bit more into the weeds, and here I'm going to present some equations that will be very familiar to you if you're not, or if you're familiar with the Kalman filter. If you're not, please bear with me. I'll try and walk you through some of the details here about why that identifiability concern might rear its head when we're trying to build a filter that works to estimate the time delay. So as I said, usually when you're dealing with filters and you're building a filtering system, you depend on the underlying system to be both observable and or identifiable. for states and parameters respectively. And here I've shown you that, in fact, the time delay is not identifiable, and that actually also means that the state here is not observable in a period less than the true delay. Now, that doesn't mean that it's not bounded. It is bounded. That is certainly true when you have bounded controls. However, it is not uniquely identifiable, or it being the state or the time delay is not observable or identifiable within the delay period. Okay, so jumping ahead, without presenting all of the Kalman filter equations in the interest of time, we can look at the innovation variance for the Kalman filter here. And the innovation variance is a measure of the effectively the uncertainty that's expected with the measurement updates. It's the uncertainty of the innovation process, which is a discrete time process in this case, because we're dealing with a hybrid extended Kalman filter system. And so I'm just presenting you with one part here, which we'll call S sub k for a simple system. It's a scalar, and I'm going to talk about this in some detail. So the innovation variance would normally be used to compute the Kalman gain, and then the Kalman gain is used to update the states and parameters of interest. And so I'm going to claim that because the delay is not identifiable, and because of the structure of our measurement Jacobian, which here is represented by the capital H, we're going to run into some problems with filtering using this particular equation. So many of you will recognize R here is just the measurement variance. So the actual measurement, in this case, it's a measurement of our position state. So our single state, the underlying position, and we can set R to whatever we like to tune it for our application, but I'll argue that you can't tune R in the way that we need to without some additional complications. So then the second term we have here in this sum to compute the innovation variance is the projection of the state uncertainty, so state and parameter uncertainty, into the measurement space. And so the covariance matrix for the state and parameter here, in this case x and tau, is P, and the Jacobian matrix H is going to transform that into the measurement space from the state space. So nothing fancy here, and we're just ignoring the fact that the Kalman gain would be computed later from this and used to update the system state. What we really care about is the fact that the innovation variance should represent the true uncertainty of the innovation process. That's the important thing. But when you actually work out the form of the measurement Jacobian, in this case for the simplified system sigma that I showed you, or for a VINS-based system, in all of these cases, what you end up with, because you have the time delay as a parameter, you end up with a situation in which you have to linearize the system, and you actually have to incorporate the most recently available control into the measurement Jacobian. So this is very strange, because in a normal EKF implementation or any other type of filter, the control input is completely separate from the measurement, right? You don't need the control to form the measurement Jacobian. In this case, you do, and that's simply because tau shows up in the measurement equation, and you have to perform a Taylor series expansion, and when you do that, you end up needing to incorporate information about the rate of change of the state, and the only way to do that is to use the available control that you have at the most recent time that you are able to measure the control. And that's really the key here. So if we look at the form of the measurement Jacobian H, we see that the most recent control U appears, but there's no guarantee that this control value U is going to be close to the control that is actually applied at some point earlier or later in time. And the example I would give is the following. Just a simple example where here I'm going to say that the position of our say quad rotor is at the midpoint of this real axis in one dimension. So x of t is going to be right at the middle with that little dashed line. And I'm going to argue that really what we should be concerned about in this case is the reachable set from that point, given the controls we can apply within the delay window we care about. Because what could really happen in practice is, with a quad rotor, for example, I could go from a thrust of hover to a maximum thrust value for the system within the space of a tenth of a second, or maybe 2/10 of a second. And so that's that's on par with what a delay range might be in a system. And so it's not exactly the case that the innovation variance, or the uncertainty in the innovation, should be a function of the most recently applied control, which is what we get when we linearize. In fact, I should be willing to accept that the system that is beneath, that is hidden, that's unobservable, the unobservable system could be in any state that's reachable, given the maximum applied control that I can input. And there are some ways to adjust this, but really what I would like to do is I would like to capture with a Gaussian here, just slapping a Gaussian on top, that this innovation variance does a reasonable job of approximating the reachable set, right? Covering the reachable set. But what occurs in practice if you have, for example, a very small control value, for example, at the last measurement update or the last control update, when you last received an update from, say, your IMU, what can end up happening is that you end up with a Gaussian that is much more narrow. And so what can happen in this case is that the innovation variance ends up being much too small. And this would not be the case if we didn't have a delay in the system. But because we have a delay and the Jacobian we build is based on an applied control, and because that applied control can be very different in the future or in the past compared to where it is, quote unquote, now when we measured it for the most recent underlying update to, say, the IMU measurement driving the process model. Because of that difference, I'm arguing that really the uncertainty we consider should be larger than in practice, according to these equations. Now, it is also true that you may actually have an innovation variance that's too large if you do the opposite thing and estimate the control to be much larger than in fact it is. But in general, we find that estimating values and uncertainties that are too large will make the estimator inefficient potentially, but it will not, in general, jeopardize the entire navigation algorithm. Whereas if your innovation variance is too small, then you start getting spuriously large Kalman updates, which I'll talk about shortly. The gain is too large, the updates are too large, and you can get some really inconsistent and biased results. And in the end, you may in fact even break your navigation algorithm. Okay, so that's my argument for filtering and considering delays in the innovation variance of the update step, and that then feeds into the Kalman gain computation, and it feeds into later steps in the process, of course, as well. So that's one issue. The other issue is problems with process noise. So when we consider state propagation, process noise, and shifting delay estimates, we recognize that the EKF prediction step always propagates the state forward from the last time step we had up until the current time t sub k. And generally, the way the proposals in the literature work so far is to propagate the state forward up until the most recent time step plus the predicted value of our delay. So a tau with a hat k minus 1, the last update for the delay value that we had from the estimator. So we're going to push the process model forward in time as far as we think we should, based on the current estimate of tau, and then we're going to apply our measurement update. Now, the problem with the process noise step, and this becomes very apparent if you consider the fact that unlike most states that are functions of time, the parameter tau actually affects the time itself. So this is usually what's the independent variable in the filter, right? We are trying to shift values, on the real line that are quantities that are usually independent, or normally in a measurement are independent of time. And instead, if you think about the x and y axes in a simple filtering problem, we are in some sense not just jiggling y, we're actually attempting to jiggle x. Right? And this is never done in practice in a normal filtering system, where time is considered to be completely independent. And so this also leads to problems because The most straightforward way to update the delay estimate and the state estimate is shown here on the slide in step 2 here. So at time index k, we're going to use the latest measurement to update the state based on the residual, which is r sub k, and the Kalman gain, k sub k. My apologies again if you haven't seen the filter equations in detail previously. Just suffice to say here that what I'm doing is I'm updating both the state x and the delay parameter tau based on the most recent measurement. And when I do that, right, when I shift the value of tau, I'm never going to shift it in a way that is perfect, right? By definition, given some noise, there's like zero probability exactly that I will get the delay perfectly correct. And so since the delay update is never exactly correct, when I shift my value of tau from tau hat k minus 1 to tau hat k, when I do that update, then on the next cycle of the filter, I have to propagate the system forward. Normally, I would do that by adding process noise to express my ignorance of the underlying system dynamics and other noises that might be involved, etc. But the problem in this case is that I'm going to attempt to tune my process noise, but the interval over which the process noise is added will also vary, and it's going to vary on a per cycle basis. And so if I have a constant amount of process noise that I am adding, the interval over which I add it will vary. And it's quite possible that this integration period may bounce. It may be a little bit too long, then a little bit too short, then a little bit too long, and so on and so forth. And the duration of the integration period depends entirely on the measurement updates and entirely on the random noise that is encountered when the filter is operating. And so this bouncing around is generally a very bad thing because it makes tuning of the process noise difficult or impossible. I don't want to crank the process noise up too much, assuming that the intervals will always be too short, because then I'm effectively overweighting my measurements. And likewise, I don't want to make the process noise far too small, assuming that the measurement intervals will be too long, and thereby jeopardize filter consistency by ignoring measurement updates effectively. So this process of bouncing around, no pun intended with process, the process of the process noise is difficult to tune, and it hints at something that's fundamentally wrong, I think, with this type of filtering-based approach. We're actually jiggling a value in time that is related to time, and so this is quite different from what we do in the normal EKF, and indeed it can lead to some pretty nasty problems. And so we should think about this as a potential red flag, right? So the fact that we are looking at trying to tune a process noise term that cannot be both too large and too small at the same time, again, sorry, referring to time twice, is something that should make us a little bit nervous about how these systems operate in this filtering context. Okay, and so there's a logical conclusion of this issue with process noise, and we can talk about delay updates and causal processes. So again, just reiterating what I said in the previous slide, the EKF prediction step propagates the state forward in time, and then at time index k at a discrete point, it gets the latest measurement update. So we saw those equations before. And as I noted, there's an induced shift in the delay parameter tau, which varies the time over which we would integrate process noise forward. But also, if you look at this quantity that I'll call delta tau, which is simply the difference between the most recent value of the delay and the value of the delay on the last update, there's actually nothing that prevents this in this entire filtering framework. There's nothing that prevents this from being a fairly large positive quantity. And what does a large positive quantity mean? Well, it means that the filter is actually apt to, in certain cases, granted subject to a rare probabilistic occurrence, the filter is apt to jump forward in time sufficiently far such that a measurement that has come in most recently can actually already be in the past. At the time it is incorporated into the filter. And so this is a very strange thing. It's difficult to describe, but you actually do see it for this very, very simplified system. that we have discussed, and it is unlikely to occur as frequently in an actual VIN system, um, simply because of the second order nature of that system. But nonetheless, it can occur. There is nothing in the filtering framework that prevents this from occurring. And so if the filter suddenly jumps forward, that is the time index represented by the filter, or time of operation, if you will, of the underlying system is represented is jumping farther into the future, then we have a measurement that should have already been processed, right? We can't actually we can't retroactively process that measurement unless we roll the filter back, which is another hassle and headache. It's another complication, right? And if we just naively incorporated this, right, my little DeLorean here is going to tell us that we would actually be trying to push the process model backwards in time to try and go backwards to the time of the last actual measurement from, say, the vision system. And that is something that we never have to do in a regular EKF, right? The EKF and other related filters are always built as causal systems where the state is only propagated forward in time. Uncertainty grows with time, and it's really not clear how we should incorporate that into this kind of this ability to jump past uh, the next measurement. How we should incorporate that into the filtering framework. Now, it's a bit technically nitty gritty. It's in the weeds, but you should be aware that even for some of the simulation trials we've done for the simplified system, this actually does occur in practice every so often, that you actually end up with a situation where just due to the random noise and even with a reasonably limited amount of random noise added to the position estimates, or position measurement estimates, I should say, right, you get this weird situation occurring. Okay, so again, another red flag that maybe we have to rethink how this is actually occurring inside the filter, and how we might mitigate this or use a slightly different approach to avoid these kinds of problems, because again, the EKF was not built in general to deal with time as a quote unquote dependent variable. All right, so now I wanted to sort of give you some proof in the pudding, as it were, with a couple of simulation studies that actually show you what happens when you simulate this simple system. And so I'm going to give you a set of two examples that I will claim have not been cherry picked. So these are relatively random examples from a series of 1,000 or more trials that we ran of the simple system with again some fairly reasonable measurement and process noise, and with a series of sinusoids as inputs. So I'm going to treat the control inputs as simple sinusoids, and then the actual true position here, which I've shown on the plot in the upper left, is also going to be a sinusoid in time. Right? So this is the true position of the system, and you can see that the dynamics here are fairly benign. I'm not introducing any kind of discontinuous spikes or anything of that nature. This is a very reasonable system by filtering standards. And if you didn't have a time delay, there would be no issue with estimating, obviously, the state of the system. It would be fully linear, and you could easily do this with a standard Kalman filter. So in this case, for these simulations and for the results I'm about to show you, the time delay was 5.9 milliseconds, and we're getting a time update at a measurement update, I should say, at a rate of 1 every 100 milliseconds, so 10 hertz. So this time delay, tau, is a very small fraction of the measurement update period, and that's important as well. And I'll initialize the first value of tau that I have, tau sub 0, to be exactly 0, because we have no other information. The best thing we can usually do in practice is just to set the time delay to be 0, assume things are synchronized in advance, and go from there, because 0 is really as good as any other quantity. So that's how the system was set up. And now on the left and the right, I'll show you some estimates of the position and the time delay and their associated 3 sigma bounds as computed by the EKF for the simple system. So this is just a vanilla EKF running for the very simple system sigma that I showed previously. That's in the left-hand column. And then in the right-hand column, I'm going to compute 2 statistics that are good indicators of filter performance. One is the normalized innovation squared, and one is the normalized estimation error squared. These are 2 standard measures or statistics that gauge the consistency and basically effectiveness of a filtering algorithm. And so on the left, you can see that the position error remains within the 3 sigma bounds, and that in part is due to some work that we did in advance to tune the process noise, and also due to the fact that the time delay here is very small. In fact, what happens is that it is not the case that the filter fails to predict and to estimate the position state well or reasonably well. That is in fact consistent in this case. And you can tune things such that, at least for these simplified systems, the position state is estimated reasonably well. You can also do things to adjust the noise terms such that you can make the filter break quite easily, much more easily than in the case without the time delay. But in this case, we haven't tried to do that. We've just tried to keep things fair and just focus on the estimate of the time delay. So speaking of the estimate of the time delay, in the lower left plot, you can see that there is a large jump in the estimate of the time delay at the very start of the operation of the filter, and that is when we've already tuned the filter such that the initial delay uncertainty is very large. So we're trying to mitigate this problem of becoming inconsistent immediately. And this is what's also been done in the literature. We generally see literature showing initialization with a very large delay uncertainty, and that can actually help to avoid filter inconsistency overall. But you'll notice here exactly what happens. So within the first update, right, the estimate of the delay jumps up, and then it's almost immediately inconsistent. That is, the estimate of the time delay, the error, the absolute value is outside of the 3 sigma bounds. So in this case, it happens to be above. So there's a specific shift that remains sort of fixed after the filter gets operating. But the important thing to notice is the qualitative behavior of this curve. So you will see that the estimate does get better as time goes on, all the way up to 100 seconds. But in general, the filter becomes inconsistent and then does not respond to new measurement updates. And so indeed, at the 100-second mark, after this filter has run for 1,000 measurement updates, so 10 hertz times 100 seconds, the estimate never recovers. It effectively asymptotes to a biased delay value. And this is very, very common. In fact, in most of the simulations we do for this system, this is what we see. Even for this benign case, it happens in about 8 to 9 out of every 10 trials that the delay estimate is inconsistent for this position curve with a certain set of control inputs and for random noise. And this is actually borne out by the 2 plots on the right. So we would hope that in the normalized innovation squared calculation, we would end up with a value that's very close to 1, because the quantity that we're looking for, there should be a chi-square distribution with 1 degree of freedom, and so we should have a value that is very close to 1, ideally. And it's not uncommon for the normalized innovation squared curves to bounce up and down, but these spikes you see jumping above 3 and up to 4 and 5 are not the best sign. They do indicate that there are points in time where the normalized innovation is a normalized innovation squared, is too large, and this is part of that red flag about filter consistency. And then, more importantly, if you look at the lower plot, you will notice that the normalized estimation error squared here for a 2-state system should be a chi-square distribution with 2 degrees of freedom. So this number for the knees should be somewhere around 2. Maybe a little more. It's squared, so it does, the knees value can creep up quite quickly. But the fact that we're seeing knees terms going up to, or knees quantities going up to almost 100 is an indication that the filter has become seriously inconsistent. And this is generally a bad thing. Now, it does get better towards the end of the run, towards 100 seconds, but it's still very concerning. And indeed, this knees plot just confirms that the time delay error is is inconsistent and remains so even after 100 seconds. I've only shown you 100 seconds here, but it is in fact the case. If you run these simulations out to 1,000 seconds, really nothing changes. The Nice plot just asymptotes as the 3 sigma bounds basically converge because you continuously are adding more information, and it just doesn't get any better. So in this case, the time delay remains biased at somewhere around 0.3 milliseconds, so 300 milliseconds. That's really quite a large bias, and it never gets better. Okay, so that was one system with a fairly benign input. Now I'm going to show you an identical set of simulations, again, where we ran many of these, and I'm not cherry picking. This is just one of many that exhibit the same kind of behavior. So here we have a larger value of the delay, negative 84 milliseconds. So this is a case where the position updates lag the control inputs to the system. Again, we've initialized the system with a delay value of 0, and in this case, we're using what I would call a slightly more aggressive control input, which is effectively a velocity control. You can think of it that way. Again, the control is just a sum of simple sinusoids, and as such, the position output is just a sum of simple sinusoids. But here you see we have a low frequency sinusoid with a higher frequency ripple sinusoid on top. So the actual accelerations, if you will, in this system are larger, and so it's a bit more aggressive if you were thinking of this as say an aerial platform. So plotting exactly what we plotted before, we can see in this case with a larger time delay and the slightly more aggressive trajectory, what we end up with is a case where with the same process noise and measurement noise parameters that we used previously, so without altering those tuning parameters, we end up with the plots you see here. So in this case, the position error comes much closer to the 3 sigma bounds, although it does not cross them. That makes me a little more nervous. And then you can see again behavior for the time delay that is very common to many of the simulations we've run, where here the divergence is even more severe. So apparent divergence, that is divergence to an incorrect quantity, that occurs very quickly, right? You can see that the delay estimate becomes rapidly inconsistent, potentially due to that issue with identifiability. And once the time delay estimate is outside of the 3 sigma bounds, it again asymptotes, but to a value that is very far away from the true value. In fact, it's almost 400 milliseconds here, and it's actually in the wrong direction as well, has the wrong sign. So again, looking at the normalized innovation squared plot, we see that there are spikes here that are now reaching up to about 7 when the value should be 1. So that's a red flag that we're seeing performance that indicates we should do some more tuning or that things aren't working properly. But in this case, the way of actually performing that tuning is highly unclear. And then again, here, because you see such a large divergence of the time delay estimate from the ground truth quantity, the normalized estimation error squared it grows very rapidly to a value of 1600 by the end of 100 seconds. Continues to get worse if you follow beyond that time. And again, the ideal value we would have here is a normalized estimation error squared quantity of 2. So this indicates really severe inconsistency in the filter. And of course, no matter how long you run this system, unless you restart it or reinitialize in some way, you will never have a time estimate, a time delay estimate that converges. Right? You just have to restart. Now again, we could perhaps tune for a specific scenario, but the issue is that you don't know when you're building these systems often what the delay is. You don't know what sign the delay has, and you may not know how to inject process noise or how to inflate measurement noise in such a way that you actually capture the system dynamics, ensure in some sense conversion of the delay error, and actually maintain your state estimate as something reasonable. You have to try and do all of these things. And my argument in this talk is really that we should carefully consider whether this is the right way to solve this problem. It may work in certain cases, it may work for certain systems, but the theoretical underpinnings are very shaky, I think. Okay, so to end the talk, now that we're just about, I think I'm a little bit over time, so I'll end up here for today with an argument that maybe we should reconsider the filtering-based approach to this problem. So the things we've discovered in this talk are that the time delay is not instantaneously identifiable, and I gave a bit of a hand-wavy proof of that, but I'll point you to a better source for the proof on the next slide. So because the time delay is not instantaneously identifiable, and we usually make the assumption that these types of things, these types of quantities are identifiable or observable instantaneously, we need to look at that very carefully. We should consider the fact that the measurement Jacobian depends on the applied control, and that we may not know the applied control at the time that a measurement arrives because of the time shift, and that the control may be quite different, and so that instead of considering the standard approach to tuning measurement noise, for example, we should actually consider the fact that the system can be anywhere within its own reachable set, which is very easy to define for the simplified system I showed you here, but much more difficult to define for more complicated systems. The result of this issue with the measurement Jacobian is that the innovation variance may be too large or too small. And I've put small in italics here because generally the case we care about more, which leads to inconsistency of the filter and the need to restart or just throw the whole thing away, is the case where uncertainties become too small. Right? So we're concerned about cases where things are too small. We're overweighting our updates effectively. I hope I've convinced you that there are some problems with process noise in general in these systems and the way they've been, the process noise values have been incorporated. And then with the simulation studies for the simplified system, I've shown you that the EKF is certainly prone to bias and inconsistency in the estimate of the delay parameter, and that this could potentially be very bad news for a real-world system. It does show up less in higher order systems, that is, systems with dynamics that are controlled by acceleration or jerk or higher order terms. But this underlying structural issue, or structural issues, I should say, these are present in all of these filtering type frameworks, just by the nature of the type of update we're trying to do of a quantity that is no longer effectively independent of time. And so, what can we think of as some alternatives to this? Well, I think there's some interesting work still to be done in this area, and certainly I may have let you down at the end here by not giving you an answer to how to solve this problem, but there's certainly interesting research that could be done. So we could use a sliding window method that covers the delay interval, and that may allow us to do this type of estimation in a more solid manner. But then again, at the expense of having a delay estimate that is not quote unquote online, where there's a lag with the delay estimate. There's been some work on observers for time delay systems. That may lead to some interesting alternatives that maybe have provable convergence guarantees. It depends. One example of a possibility that's been suggested to me is to consider something like an H infinity type filtering framework, where it's a game theoretic worst case analysis, which could allow the time delay to be more robustly incorporated into this type of a filtering setup. And then there are a number of other approaches that could be explored: set-based techniques, interval analysis, and so on and so forth. So I would love to encourage the community to think about some of these possibilities. So just some conclusions to tie up at the very end here. In this talk, we basically, I say we, myself and the co-authors of the paper I'm about to show you, attempted to lay out some fundamental concerns with the filtering-based method for time delay estimation or temporal calibration of VINs and of other multi-sensor systems where delays are present. And I would argue that this is perhaps not all that surprising, since, as I mentioned earlier, time is usually considered to be the independent variable in all of these filtering frameworks. So if you think about, again, X and Y axes, all the measurement stuff occurs on the Y-axis, and in general, nothing is meant to affect the X-axis. But when I introduce this tau parameter, that is a tau, a shift that occurs in X, not in Y. That is along the axis that is normally considered to be independent. So if we were looking at this in a total least squares framework, what you would probably consider is something called total least squares, right? Or an errors and variables model, and that is not generally incorporated into the filtering setup. So I think there are some interesting alternatives that could be explored, including some types of observers that have certain convergence guarantees. That's a possibility. And if you're interested, actually, we do have some more details about the material I've gone over today in the MFI conference paper submission that we submitted to this year's conference 2021, a question of time, revisiting the use of recursive filtering for temporal calibration of multi-sensor systems. That's on behalf of myself, my co-authors, students in my group, Chris Greb and Matt Gamu. And there's a preprint available on arXiv at the URL here. If you'd like to take a look, I'd love to hear your feedback on the paper, and we'll see if it is accepted for MFI or not. And with that, I'll close. Thanks for bearing with me as I've gone a bit over time. And I just wanted to take a picture again in the hotel and give you a big thumbs up to the organizers, to the attendees, and to everyone for doing a great job with this. The constraint of a virtual event. I'm grateful for the opportunity to speak with you today, and I would love to hear your feedback as well, and hopefully see some really exciting future instances of this workshop coming up where we discuss time delays and other VINs related things in more detail. It's a fascinating topic with lots of real world applications, so I love working on it. All right, thanks very much, everyone. And again, hope to see you either virtually or in person at the next conference or symposium. Take care, and we'll talk soon.